Hello everyone, welcome to the first lecture of week 3 of the course Simulation of Modern Power Systems, in which we continue our discussion on the first module, Power Flow Analysis. And in this discussion, we'll take up an interesting topic. Often this topic is not explained at length in conventional textbooks, although great amount of research has been done in the literature papers that one would see and explore and can get furthermore insights of what this participation factored power flow is. As I was explaining in the previous discussion towards the end, that instead of dumping all generation load mismatch, as well as system active power losses, both real and reactive, on the slack bus or single slack bus, it's often uneconomic because that's not how actual system operates. Because given a power network with multiple diversified generators, why should only one generator be responsible for taking up the entire network loss? This loss is coming up because there are different loads present. Different generators are trying to satisfy these different loads, and this is what is creating this mismatch and loss difference. So why only one generator should be responsible? And that is where uneconomic aspect of operation comes in. So this discussion today will start with very basics of or brief discussion on economic dispatch, and then I will tailor the discussion toward what this participation factored power flow is. To sort of give you a heads up, in participation factored power flow, we will have more than one bus acting as the effective system slack bus. The angle reference bus, it remains unique, but the slackness concept, which is basically accommodating generation load mismatch and loss, that mismatch will be shared by more than one generator depending on their economics of operation. So the last discussion, we have concluded with the Newton-Raphson method application for voltage phasors when they are represented in rectangular coordinates, and we had seen an exhaustive example. I would request the viewers to please solve or have handwritten practice of the example that I have discussed. That will make things further more clear. In today's discussion, we will solve participation factored power flow using Newton-Raphson method with bus voltage phasors in rectangular coordinates, so that the discussion that we have had for bus voltage phasors in rectangular coordinates, it easily gets furthermore solidified, and the explanation of participation factored power flow also becomes clear. It's not that participation factored power flow can only be done for voltage phasors in rectangular coordinates. It can also be done or solved when voltage phasors would be in polar coordinates. The discussion, however, would remain the same. So where is this economics or cost operation coming in? Why generators have to sort of look at the economics aspect? The reason is that in a given practical power network, we have generators present at different locations. The generators are of multiple types. We have hydro, thermal, nuclear, renewable energy resources. These generators, they have different locations of different variety. The loads also are differently placed from these locations. It's not necessary that wherever we have generators or plants, the same location we have loads also present. These generators, since they are of different types, their efficiency, operating efficiency is different. They have different ramp up and ramp down limits. By ramp up and ramp down limits, I mean that if a generator is operating, let's say PG at the given instant of time, and it has to increase its generation from PG to, let's say, PG1, then the time required for this generation to change from PG to PG1, it is not instantaneous. Every finite physical generator has limited ramp up capacity, which means that it would require significant, or I would say appreciable amount of time to change its generation from PG to PG1. Similarly, if the generation has to go down let's say from PG to PG2, then this also requires some time, which is measured in terms of the ramp down limit. So basically, if I have to say or define ramp in absolute form, this is the change involved in generation divided by the time involved for the generator to change its generation limit or generation capacity, and that's where the ramp values up and down aspects come in. Different generators have different ramp up and ramp down limits, different capacities. Their fuel mix technologies are different. Since the technologies are different, it's obvious that the investment cost and the running cost of these generators are also going to be different. In terms of the conventional generators that we have, hydro and nuclear plants, their capital cost is, investment cost is very, very high, given the auxiliaries and the geographical span involved in setting up a hydro and a thermal plant, but their running costs are comparatively much, much lower. On the other hand, thermal plants have moderately lower investment cost, but the operating costs are high because these are mostly fossil fuel dependent generations. Renewable resources, solar and wind, their investment cost is relatively lower thanks to the advancement in technology, and their operating cost is also low because they are all weather dependent. There is no necessarily any fuel input needed for these renewable resources to generate power, and hence the operating cost, which essentially boils down to maintenance cost, is much, much lower. Thermal plant, on the other hand, requires continuous input of fossil fuel, could be gas, coal, or any other form of fossil fuel, which are costly. They are not replenishable, and that's where the operating costs go high. Hydro and nuclear, for hydro plants, water head is the availability, so seasonal availability of water is what makes its operating cost low. It doesn't require a dedicated fuel mix to go into hydro plant for generation. Nuclear plants require uranium based or any other radioactive based element, which once procured runs throughout for a longer period of time, and hence on an initial investment basis the cost may be high, but for the overall long term perspective the running cost go down. On the other hand, we also have a similar or interesting variation from the perspective of load. You can see great amount of detail in this link which I have given here. In fact, the picture that I have shown here is taken from this link, thanks to the author of this particular web page. Typically, the load given any city, household, locality, community, country, on a daily basis, the load also doesn't remain constant. Depending on how do we live our lives, typically normal human beings, they get up in the morning and hence the load or the electrical load requirement goes up because of heating load, lighting load, electrical appliances usage and so on. After getting ready, either we go to our schools or offices, and which is where we spend our time in traveling, and as a result of which the typical electrical load tends to go down. And once we are back to our homes in the evening when sun goes down, the electrical lightning load requirement goes up, and hence in the evening hours again we do have a peak. So typically in the early morning hours and late evening hours, for any nation, society, community, the load experiences peak, whereas during off-peak hours, typically around the mid of the day or sometime in the middle of the night, the load also goes down to its minimum value. If I have to sort of replicate the two peaky behaviors and two dip behaviors with this duck that I have drawn, it very well fits the shape, and that is why daily or annual load variations for a community, residential complex, country, city, nation, state, we call, as electrical engineers, we call those curves to be a duck curve. Because of the two peaky behaviors, one peak at the tail of the duck, the other peak at the head of the duck, whereas the beak and the feet or the belly represents the bottom portion of the load curve. So since generators are different, load also has variations, and as operators, the sanctity or truth is total generation should always meet demand. We cannot leave a load unsatisfied. It would only create loss of load, would only create inconvenience. So generation has to meet the demand while also maintaining sufficient reserve so that in case something unwanted happens, such as sudden load change, bad weather, then also the generation reserve should be ready, which can easily ramp up or ramp down depending on the load requirement. We call this reserve, or one of the form of these reserves is called as spinning reserves. There are other forms of reserves also which fall in the domain of ancillary service requirement. So in terms of the dispatch, while ensuring that generation should meet the demand or load, what is the conventional thought process behind dispatching of these different generators? The conventional thought process would be, which is also called as the merit order approach in some literature, or also called as the bucket filling approach in some literature. In fact, some of our operators, they still follow this practice of generation dispatch, wherein their intent is that total generators, whatever numbers they are present, their generation should meet the total demand or load present at the network in the given system. So what is this merit order or bucket filling approach? You prioritize or rank the generators depending on their cost of operation. That is, during light loads, try to bring in or run efficient units whose operating costs, running costs are low, and as demand increases, bring in other inefficient or costly generators depending on how the load is increasing. With this merit order based approach, the merit here is basically referring to the priority, whereas bucket filling is essentially referring to the way generators are being turned on or off depending on high or low loads. Essentially, bucket is the total load which is present, and starting with the cheaper generator or efficient generator, it is turned on, and then as the load increases, the next costly generator comes up, and so on. The problem with this merit order bucket filling approach, from the human mind perspective, it would appear that, oh, I will always get the least cost of operation with this merit order approach because cost is also important. That's not true. It doesn't always result in the least cost of generation, which is where the exercise economic dispatch comes in. It does the same exercise, that is, it tries to meet the same constraint. Not tries, it essentially meets the same constraint while also looking at individual generators' cost operation and also foreseeing that in the next instant of time, what would be the expected load change. Rather than waiting for that time to come in, economic dispatch pre-plans things and helps the generators to get scheduled while maintaining sufficient security and reliability, which comes from the aspect of the fact that, one of the facts that different generators have different ramp up and ramp down limits. If as an operator, I only look at the present condition and think that the next condition would be automatically taken care of from system operation perspective, no, that's not how generators should operate, which is essentially what is missing in the merit order or bucket filling approach. Economic dispatch, on the other hand, pre-plans this while ensuring least cost of operation, specifically for thermal units, where the corresponding ramps are very, very high, and also ensures sufficient security and reliability. So question comes is, why thermal units are so important or tricky or essential in economic dispatch. Often nuclear units, since they are radioactive based generations, so often they run as base plant. That means their generation doesn't change usually due to safety concern. Hydro units have low operating cost and they can easily respond to load change, which is where they have fast ramp up and ramp down capability. Thermal units, on the other hand, their costs are high, their ramp up and ramp down limits are also slow, which means they would require sufficient amount of time to change the generation value. And hence, it is often difficult to pre-plan or preset what the thermal generation schedule would be. Economic dispatch, as I mentioned, it plans ahead in time and gets ready with what the schedule would be, not only looking at the present operating condition of load, but also the next instance of load that is going to come in. which is where the benefit comes from economic dispatch. If I have to discuss economic dispatch at length, there can be a dedicated course on economic dispatch in itself. For the sake of the modules that we have to cover, I am not going to discuss much of economic dispatch. I'll only briefly touch upon the economic dispatch mathematics a bit, and then we will go to the participation factor module. So what I have here is, I have drawn a model of a power network where I have n number of thermal units. Each of these thermal units, they have their own boiler mechanism, turbine mechanism, and electrical generator mechanism. And I am assuming that the load which is present in the network, it is present at the same bus. That means there is no power network involved, which is what is mentioned as ED without network. If I would have a network present, then the same economic dispatch exercise gets extended to something known as OPF, also known as optimal power flow. We will discuss also briefly about optimal power flow in the next module on contingency and security analysis. Assuming that each of these generators, PG1 to PGN, have their respective cost function, where Fi PGI is essentially the cost function dictating what would be the cost of generation. This cost of generation, please remember or note, it is not the instantaneous cost. Rather, these cost values or curves are obtained from regression analysis, and these are often not even continuous curves. This cost is basically the average cost of generation on an hourly basis. That's how the network operators or use these generation values. The objective in economic dispatch is to minimize the cost of generation while ensuring that all these generation match the load, because we don't have the network in place. Also, each generation should have its generation within the minimum and maximum limits. The minimum limit comes due to boiler consideration, whereas maximum limit comes from the turbine operation of how it can operate. Every turbine has a physical limitation on what speed it can run at. Ideally, the cost function Fi PGI can be expressed as a linear function or a quadratic function using curve fitting, while also considering the different nonlinear effects such as valve point loading effects and so on. Again, this discussion on obtaining this curve fitting is a dedicated discussion on itself. I'm not going to go into those details at length. Coming to participation factored power flow, the basis is that in single slack bus case, all generation load mismatch and system losses which are not known. Please note that these system losses are not known a priori, and as a result of which we cannot decide that what would be the system loss, because the system loss depends on line currents, the line currents depend on bus voltages. So until unless we solve power flow, we don't know what the system loss is. The generation load mismatch, it can be known a priori depending on the generation specifications and the load specifications that we have. But together, if we add these two quantities and mark it with a variable rho, then this rho variable is not known a priori, and as a result of which, in case of single slack bus, this entire rho gets dumped to the slack bus, and that is where the slack bus generation comes in. Given the discussion on economics, it is not necessary that this slack bus where the largest generator is connected is always a cheaper bus, and that is where the uneconomic operation comes in. Why should only one bus or one generator be accountable for accommodating this rho unknown variable? Why can't we have multiple generators, depending on their cost operation, share this rho mismatch so that the system operation moves from uneconomic operation to economic operation? So in low cost operation, the cheaper generator should account more or share more of this rho compared to costly generators, and that is where the factor of beta comes in, which is called as the participation factor. If I have a generator or all generators whose cost curves are linear expressions of PGI, AI and BI are the cost coefficients. AI is not 0, BI may or may not be 0. Then given this cost function, I can define what is participation factor for all n generators. or all generators which are present in the network. It is essentially a measure of how costly or cheaper a generator is. If a generator is costly, then it would essentially mean that the value of AI is very, very high. If AI is very, very high, no matter what PGI comes in, the corresponding cost would be higher. From economics perspective, this costly generator should participate lesser, and that is where beta is inverse function of AI. If the generator is cheaper, then AI is low, inverse of AI would be higher, so corresponding beta would be higher, and hence the corresponding generator can participate more in sharing this unknown rho. Again, since beta is basically an average of all such inverse cost coefficients, if I have to add beta for all generators, then this condition also automatically becomes true, which means that for cheaper generator, beta is high and it should participate more in sharing this rho, which is unknown. And that is where the inspiration of participation factored power flow comes in. If we have to realize this through rectangular coordinate of bus voltage phasors, we start with the same assumption that bus 1 is the slack bus. Its real part of voltage is same as the specified voltage, whereas the angle reference being 0, so imaginary part is 0. Also, we know the generations at all buses, all generator buses, including the slack bus also. In actual network specification, generator at bus 1 is specified like generators, real power generations at all other PV buses. On similar lines, for bus 1 also, the generator would have specified its real power generation through cost economic dispatch operation. But from power flow perspective, we intently don't use that PGI, because if you recollect our discussion on the case where we were discussing about classification of buses, slack bus discussion specifically, if all generators become specified, then it is not necessary that all generators together would match the load. Even if generation load mismatch is 0, the network will have losses. So one of the generators has to become free so that it can also account for the system losses while the load is being met. That's the reason why for slack bus, PG we don't consider in conventional one slack bus case. In rectangular version of rectangular version of participation factored power flow, if bus 1 is a slack bus with generator connected to it, we will be using this PGI specification in the corresponding analysis. The unknowns with context of rectangular version of power flow, they remain the same. That is, we have n-1 Fs, we have n-1 E's, and also, as I mentioned, because system losses are not known a priori, so rho is also unknown. This unknown gets added to the x vector. So essentially, my 2n-2 variables with one more variable coming in results in 2n-1 variables, which means that in power flow for participation factor consideration, I should have f of x, which is also of dimension 2n-1 cross 1. So where is that additional equation going to come in? Please have patience, we will see that. And that's what is mentioned here. We require one more additional equation in order to get these 2n-1 unknowns. The additional equation is coming in from the fact that if there is PG1 is specified, which is usually the case, because bus 1 is also a generator bus, so like other PV buses, PG1 would also be known, then we can include the real power equation of slack bus as real power equation of the angle reference bus as the additional power flow equation. Please note that in participation factored power flow, like in single slack bus case, we have only one angle reference bus, which we have chosen as bus 1, but bus 1 is not necessarily a slack bus. Compared to what the participation factor is for other generator buses, there can be more than one slack buses. So that's what brings in the equation number 1, I is equal to 1 case also. With known participation factors as defined in slide number 8, we bring in Pi minus PGI and the additional participation. So basically, combination of PGI plus beta I into rho is the actual generation at bus number I. PGI is called as the base generation or base value of generation, and this is the additional sharing of the mismatch rho, which is accounting for generation load mismatch and system losses. The rest of the equations, they remain the same. We had equations for buses 2 to n as we had seen for the previous case also. Wherever there is no generator present, then PGI is 0. If there is no generator present, then participation will also not exist for that particular bus. QGI for slack bus is considered to be unbounded. That means its limits are minus infinity to plus infinity. Jacobian, since the dimension of f and x have increased by 1, so Jacobian also has additional row and additional column. The process of Newton-Raphson technique remains the same. Similar equations and discussions are applicable for voltage phasors in polar coordinates. The convergence criteria also remains the same. The handling of Q limit process also remains the same. It will become evident through this example that I am going to discuss. The data sheet here or the specification here is the same system, same data as we saw for Newton-Raphson application for voltage phasors in rectangular coordinates. The difference here is that generators at bus 1 and bus 3, they will have participation factors. I will discuss two cases of participation factors, and we'll see how the corresponding process flow goes. So, given that the network remains the same, the line impedances are the same, shunt admittance remains the same. So, Y bus is exactly the same as we saw in the previous example of Newton-Raphson application for voltage phasors in rectangular coordinates. The specification sheet is also same. The difference here is that PG1, no value has been specified. So, I can easily assume PG1 to be 0. If PG1 is 0, as nothing is mentioned here, if PG1 is 0, I should also remember that since I am talking about participation factored power flow, PG1 actual would be PG1 plus beta 1 into rho, and PG3 actual would be PG3 plus beta 3 into rho. Beta 2 is 0 because bus 2 is a PQ bus, and this PG3 is nothing but 0.5. Since nothing is given about PG1, so I have chosen PG1 to be 0. Voltages, they remain in rectangular version. The unknowns have increased by one vector. We have rho as the additional vector. Initial choice remains the same as discussed earlier. Power flow equation has also increased by 1. So, we have this bus 1 P equation as the new equation with additional term present at the PV bus P equation. This is the new term. The other terms or expressions, they remain the same. The expression of P1 has been given here. For expressions of P2, P3, Q2, please refer the last discussion slides where you would find details. Please cross-check that these expressions are correct and they are consistent. Given the initial choice of variables, which is similar to what we saw for the previous case, I think here there is, I can easily choose this to be 1. So, I can easily choose the mismatch to be a 0 element, although I can choose any other random value of rho also, but that is not so important. At this initial choice of voltages, let me just cross check again. Sorry, there is a mistake here. E30 is 1.05 and not just 1. I will recorrect the slides and reshare. So, this is 1.05. Rho is 0, although it can be chosen as any other number. At this initial choice of variables and other known quantities, I'll recalculate P10, P20, P30, which numbers are given, Q20 and Q30. Q30 at this initial choice is 0.3891, which indicates that bus 3 remains as PV bus because this is the corresponding limit, and V3 is 1.05 PU. Now, I will take two cases. One case where beta 1 is 1 and beta 3 is 0. If beta 1 is 1, that means the generation at bus 1, PG1 actual, is PG1 plus rho, where PG1, if it is 0, then this becomes down to rho, and PG3 actual is same as PG3, which is exactly the case of single slack conventional power flow in rectangular coordinates. Given these injection expressions, if I use the form of f of x given here, I can find the initial value of f of x. I have this as my additional term. The other 4 terms, n terms, they are the same as we saw in rectangular coordinate Newton-Raphson power flow. The process of evaluation of Jacobian matrix, the philosophy remains the same. The difference here is that I have now 3 cross 3. I have got 9 submatrices. The 9 submatrices are of this order. This is JPF, this is JPE, this is JP rho, then JQF, JQE, sorry, I think I missed here. This is the line. Then I have JQ rho, and I also have JVF, JVE, and JV rho. The 6 submatrices, they are the same as in rectangular version Newton-Raphson coordinate. The last 3 submatrices are coming in because of the additional rho variable coming in. Since rho expression is not affecting Q2 and V3, that's the reason why these elements will always be 0. And if I choose or relook at my P1 equation, then P1 equation is actually P1 minus Pg1 minus beta 1 into rho plus PD1. This is my first f of x. If I take its derivative with respect to rho, I will essentially be left with minus beta 1. And for the case that we have chosen, beta 1 as 1, I see the minus 1 term coming here. Rest, beta 3 is 0, beta 2 is 0, so these 2 terms are 0. This is pertaining to Q2 rho. Q2 doesn't have rho expression, whereas voltage also doesn't have rho expression. So that is why these 2 elements are 0. So with this Jacobian, if I substitute the corresponding numbers and do the factorization, this is my update vector, where this pertains to F21, this is F31, E21, E31, and this is rho. The first 4 elements are the same that we saw in the Newton-Raphson rectangular version coordinate, which is what gives these voltage vectors. And in terms of convergence, the iterations remain the same, the voltage phasors remain the same, generation, and in fact rho here at the convergence is 1.4245 as shown over here, because Pg1 is 0. So rho is 1.4245. Why is rho 1.4245? Rho is responsible for generation load mismatch plus system loss. The loss has turned out to be, real power loss has turned out to be 0.4245. In terms of generation load mismatch, the demand is 1.5. Only one generator is generating 0.5. So the additional 1 PU load requirement gets added to this loss, which is responsible for 1.4245. The answer is exactly the same that we saw for Newton-Raphson rectangular version of coordinates. Now if I tweak the participation and have both generator 1 and generator 3 participating in equal share, it is 0.5, 0.5. The initial f of x 0 vector doesn't change, initial choice doesn't change. In fact, the Jacobian matrix, all these elements, they remain the same as we saw in the previous few slides. The last column, however, changes because this here is minus beta 1 and this here is minus beta 3, beta 2 is 0. With this, if I get my updates, then my entire solution vector has changed. This is the new rho after first iteration. At convergence, the voltage phasors have changed, the injections have changed, and in fact, rho is nothing but 1.3484, 50% of which, beta 1 being 0.5, 50% of this rho is being taken up by generator 1, which is making P1 to be 0.6742, just half of rho. And similarly, Pg3 is now generating 1.174 per unit and not just 0.5 per unit. The reactive power generations, they remain more or less same. Qg3 is at 1 pu, bus 3 is no more PV bus. And more interestingly, the loss has gone down from 0.4245 to 0.3484 per unit, which is essentially showcasing that with generators participating in terms of generation load mismatch and system loss, the system economics is improving. It is moving from a inefficient operation to efficient operation because system losses are low. If system losses are low with the same load, the overall cost of operation would also be low. That is where the importance of participation factored power flow comes in. The next discussion will be on fast decoupled or decoupled power flow, which is an extension of Newton-Raphson technique where continuous or every iteration Jacobian evaluation and factorization can be avoided and limited. It has its own history and uniqueness. We'll talk about this in more details in the next discussion. Thank you.